Pop quiz. You bring a p-type region and an n-type region into contact to form a p-n junction. What happens first? A. Nothing happens. B. Holes pull electrons across. C. Electrons diffuse into the p side and holes diffuse into the n side. Or D. All charges instantly vanish. Lock in your choice. We'll reveal the answer shortly. In this video, you'll learn how a p-n junction forms, why a depletion region forms, and how the junction reaches equilibrium. Before we look at the junction itself, let's quickly review the two sides. In p-type material, acceptor atoms create lots of holes, and the acceptor ions are fixed in the crystal. On the other hand, in n-type material, donor atoms create lots of electrons, and the donor ions are fixed too. The mobile carriers are the holes and electrons. For anything interesting to happen, the p side and n side must form a continuous junction, with no insulating gap, so carriers can move across the interface region. So, what happens when the two sides first touch? Imagine there's no barrier at the interface. Like gases, carriers initially spread from high concentration to low concentration. That spreading is diffusion. Right away, holes diffuse from the p side into the n side, and electrons diffuse from the n side into the p side. This is strongest, right near the junction, where the concentration changes. When an electron meets a hole, they recombine. That means the free electron fills a vacancy, and the pair is no longer a free mobile charge carrier. Recombination removes the mobile carriers near the junction, but the dopant ions cannot move, so you uncover a region with exposed fixed charges, positive donor ions on the n side and negative acceptor ions on the p side. This is the depletion region. Here's a common misconception. Holes aren't tiny positive balls that tug on electrons like magnets. A hole is a missing electron in the bonding structure. An empty spot an electron could fill. We often model holes as positive charge carriers because they move and respond to fields like positive charge. Those exposed ions create a built-in electric field across the depletion region, from the positive donor ions toward the negative acceptor ions. Now we have two competing motions. Diffusion tries to move holes into the n side and electrons into the p side. But the electric field creates drift that pushes holes back toward the p side and pulls electrons back toward the n side. Early on, diffusion is strong, so recombination increases and the depletion region grows. As it grows, the built-in electric field builds up, making the drift effect stronger too. Now, time to answer the pop quiz. The correct choice was C. Electrons diffuse into the p side, and holes diffuse into the n side, because they move from high concentration to low concentration near the junction. So far, we have covered diffusion, recombination near the junction, and how a depletion region with a built-in electric field forms. Want to check your progress? Tap the link for a quick practice test and a concise study guide tailored to this lesson. Quiz yourself, skim the highlights, and jump back in. But the story isn't finished yet. Even in p-type, there are a few electrons, and even in n-type, there are a few holes. These are minority carriers, and they matter a lot for equilibrium. For example, a minority electron on the p side can wander into the depletion region. Once it enters, the built-in electric field sweeps it into the n side. The same happens for a minority hole on the n side. Once it enters the depletion region, the field sweeps it into the p side. Over time, the built-in field creates a barrier that opposes further majority carrier diffusion. At equilibrium, drift and diffusion currents balance, so the net current is zero, even though carriers are still moving. That's why the average carrier distribution stays steady. You can picture the depletion region like a barrier. A few carriers with enough thermal energy can still cross, but as the built-in field builds up, crossing becomes less likely. Here's the full feedback process. Step 1. Carriers diffuse across. Step 2. They recombine near the boundary. Step 3. Fixed ions get exposed. Step 4. The electric field pushes back against further diffusion. That feedback is why the junction settles instead of mixing completely. Here is a mistake. Thinking you can just glue two semiconductors together and get the same behavior. The classic junction behavior assumes a clean interface with no insulating barrier. So, carriers can move across the interface. This equilibrium behavior is why PN junctions are so useful. Applying an external bias can lower or raise the barrier, so the junction conducts much more easily in one direction than the other. The basic idea of a diode. To recap, carriers first diffuse across the junction and recombine near the boundary. That exposes fixed dopant ions, creating a depletion region and an electric field. Equilibrium happens when diffusion is balanced by drift driven by that field. Now that you've watched the video, let's see how much you remember. Head to the link in the description, where you'll find Quizlet content made just for you.